Greetings again, this is Scott, known as Cantaloupe to some, with another video, and this one is going to cover some of the things I do in programming for graphics and games, and it will cover a couple of important things like creating a basic canvas shim for graphics, for 3D graphics, how to handle something called responsive web design with regard to the canvas, which means it appears consistently and sensibly on a variety of devices, mobile and laptops, PCs, that kind of thing, without any huge problems. Responsive is kind of an art form. And I've explored quite a few solutions and finally arrived at one, which is basically setting a fixed width and height for the canvas, so I don't have to worry about the canvas itself resizing. It's always going to be the same aspect ratio, that is the width to the height ratio, and then I just work within that rectangle, and I resize the rectangle and center it basically on the screen, which is more challenging than it may sound sometimes. So I'm going to show you how to do that, and I'm also going to show you how to do a little bit of math, some 3D math. It's going to be a real quick video, but it's going to cover a function that I use a lot. It's one of my core functions that creates the graphics, the 3D part, the perspective of it, and I'll describe it as the video plays. So here we go. I'm using CodePen for this. It's a free website. They have a premium version that you can subscribe to. It starts you out with a basic template. As you see here, you have your three HTML components. You've got HTML, your style sheets, CSS, and your JavaScript. For a static website, those are all that are involved, surprisingly. You can add some other things, but it all kind of boils down to those three main components. So I'm going to get started with some style. It's going to apply a background to the body and the HTML element, which are the containers for everything else, basically. We're going to assign it a width and a height, because it doesn't necessarily have one in all browsers. So we're going to start with that, and then notice there's scroll bars on the right and bottom. We're going to omit those with the overflow hidden, and that will take care of our overflow in case there is any. So we have a black screen basically, which is a good starting point. And some browsers inject their own margin just for style, because they like to do that, so I set it to 0 because that's what I want. We added the canvas element in HTML, give it an ID of C just for brevity. It's going to be the only HTML element in this program. And then the style is going to just have a background of a hex code. It's a short hex code of 1, 2, 3. I can explain that, or you can look it up later. But notice it appears in the upper left by default, and that's just because of the type of element it is. And we don't want that. We want it to be in the middle, so we're gonna put it in the middle with left 50%, top 50%, and position absolute, which means it's not going to be dependent on anything else. And then we want to actually center it, because that's the upper left corner is in the center. And now to center the actual object, we're going to transform it by negative 50%, which is relative to itself. So now the whole thing is centered, but it's not quite the right size. We're going to want something that's bigger depending on the viewport that the device has. So we can hard code a width or a height, as you see, but that's not responsive. See, once you hard code a width or a height, obviously not everybody has the same screen size. So we're going to want to read the screen size basically. We're going to do a little JavaScript in the background, which is run when the page is loaded. The JavaScript that is included on the page runs automatically. It's just part of the website or the web page. So we're going to look at the console here, and just check the output. So we just grabbed the descriptor IDC, which is our canvas, and you can see it shows up in the console, and if we hover over it with the cursor, it shows us what's selected on the screen, which is kind of handy. Most browsers do that if you output that. And you'll see if we resize the window, our square doesn't change, and that's what I'm talking about with the not being responsive yet. So we're going to fix that. We need a listener. We're going to add a listener on the window resize, and we're going to just check to make sure that listener is working by outputting the width of the body, and you can see it's working. The console's showing that the body width is changing as we change it, as we resize. So now we want to define a constant that is a target, basically, for our aspect ratio. I said I'd like to work with a rectangle, and a common aspect ratio for screens nowadays is 16 by 9. So you find it everywhere. It's not the only one, but it's a modern one, and it's very common. So we're going to grab the actual aspect ratio, abbreviated by the variable AR, and we're going to just look at what that ratio looks like that we want it to be. It's going to be 1.777 ad infinitum. So that's our target, and we can use that, or we can just use the math, which would be 1920 by 1080, which is the common pixels that we would have. So now we have a little bit of logic. If the aspect ratio, the current aspect ratio, is greater than our target, then we are going to size it one way. That is, another way to put this is if it's going to be portrait or landscape. We're kind of detecting if it's going to be a portrait or landscape screen. With regard, and our portrait and landscape isn't based on a square like a normal portrait or landscape orientation would be. It's based on a rectangle, like we just described. So the code here is a little bit dense, but it's checking for whether our rectangle better fits vertically or horizontally, and it's going to resize it accordingly. So in just a moment here you'll see, well, we have to call this function. We want it to be called at least once when the program runs. So right now it's a listener when the window is resized, but we want to actually call it. So we just add a little variable name before the function, and then we call that variable right after the function. So it's actually being called automatically when the program runs. And you'll notice that I made an error with the case on one of the properties here. So the W needs to be capitalized. And once I do that, you'll see it's now resizing and it's centered. And we now have a fully responsive app. But there's nothing in it yet. So we have a canvas that's centered, and it's always going to look centered, and it's going to be fully on the screen as much as possible. We may want to add, just for aesthetics, a margin, so it's not just right up against the edge of the screen. I kind of like to do that, and that's super simple to do. I'm going to add that real quick here. You can do that intuitively by adding a style margin to the element, but that kind of pushes it off screen. Remember, we're working with the upper left corner most of the time for elements. It's going to be relative to the upper left point of whatever you're doing. So we have to do a little subtraction, and some of that will be pretty obvious. Let's see here. Oh, actually, I didn't do the margin, but I can add some code to that. If you want to check the link after the video, I will add the margin, and it will be in there, and you can check the code. So you have a red square, and you'll see that we can easily reposition it. And we're in a main loop here. I want to describe what's happening on the screen. There's the loop is being called. It's called draw, and it's not actually looping because it's being called once and it's drawing the square, the rectangle, and then it's ending, basically. There's no animation or no possibility for animation. So what we're going to add is a function that is provided with the HTML5 API, the Canvas API. It offers this. It's a really handy function called request animation frame. And what this does is it gives you a place to put in a function name, and it's usually the function where you're putting this call. So it calls itself. It's called recursion if it's calling itself. And it's going to exit the function with an intention of recalling it as fast as is needed to achieve 60 frames per second. Now, there's a lot of stuff that happens in the background. This is included with every current modern browser. So you can see it's happening right now. You can see that it's targeting 60 frames per second, and we know this because we just put a variable in there called t. And t is being incremented by 1/60th, and it's counting up once per second. And now we have a loop. We have a proper animation loop, and we can do things inside that loop. And the little condition here, if not t, means that if t equals 0, or if it evaluates to false, in other words, do something. Otherwise, it doesn't get called. So the effect is it gets called once. You enter the loop, t is 0 at that time. It's a handy way to initialize things once, global variables, for example, or a function that you don't necessarily want to redefine more than once. So I'm going to put my new function in here. It's going to be defined once globally and never again, while the program is running. And this one is pretty dense. I can give you a quick overview of what's happening here. This is the product of a great deal of research and time on my part into geometry and 3D math. But what's happening basically is it's trigonometry. If you're familiar, it uses a hypotenuse function. It's a built-in function, but you don't need to use the built-in function necessarily. And it uses sine and cosine to perform rotations. It accepts, you'll see the parameters it's looking for. One second, once I scroll back down here. I'm adding shortcuts to sine and cosine. So S is, you can assign it globally as math.sine, which means you can use that function with the letter S, which is shorter and easier to remember for me. It's what I do, but you can use whatever notation is comfortable and familiar to you. So what it's going to do is it accepts 4 parameters. You see there's roll, pitch, yaw, and im. What this is doing is it's preparing to accept some input, right? It's a function, and you're going to pass it some values, and then it's going to do something and output something. That's what functions do. You give them information, and they output something, or they do something. So it's going to do basically 3 transformations every time it's called. And you see here I have 3 pairs of math statements, basically. And what it's doing is it's rotating parallel to the 3 main axes of a 3-dimensional space. So you have roll, pitch, and yaw, which you may have heard of. They're pretty common. Don't need to describe those. You can look those up if you want. But you can optionally send it values. They're called radians that you would use to rotate around these axes. So M is just it's called a Boolean in this case. I'm using it as a Boolean, which means true or false. It's a single bit, and if it's non-zero, that means it's true. And if you include m, or anything that's non-zero, for the 4th parameter in this function, it's going to add the value of the globals OX, OY, and OZ to your output, which gives you a nice quick and dirty camera, basically, so you can back off the camera from whatever you're drawing. And otherwise you'd be in like right in the middle of it. Whatever you're drawing is, you can't see it because you're like literally in the middle of it. So you see here, I'm just throwing some sine and cosine data together. It's just a for loop. It's going from 3 to 0. If you're familiar with for loops, it ends when I gets to 0. In this case, if you see how it's set up. So sometimes you would count up, sometimes you would count down. Either way, it's fine. It makes no difference in this case. I'm assigning the globals that I spoke about, OX, OY, and OZ. And then the roll, pitch, and yaw are also globals. Some people don't like globals, but for my apps, there's no problem. I know what they do. I know their scope, and it's fine. I use them constantly. So big conversation. But so now X, Y, and Z are also globals, and that's also important because when I call this R function, it's going to do the math on X, Y, and Z, and it doesn't return those values. It's just understood that they have been changed potentially, or else not potentially, definitely, because you called the function for a reason, hopefully. So you'll see after you rotate your data, whatever it is, it's 2D in this case. I'm just drawing a triangle. You need to display it. You need to project it. So to do that, to translate from 2D to 3D, and this is super condensed and simple, it's trivial here, this Q function simply takes the width of the canvas, cuts it in half, so you're in the middle, takes the height, does the same thing, so you get a center point, and then you take x divided by z. Z is your depth, right? So your x, you have an xy grid, and z is how far in front of you it is, or behind you. And you divide by z, so you're getting perspective out of it. And then you just amplify the output because you're dealing with some small numbers, and you want to give it some size, some magnitude. So a good number based on our pixels that we're using is 700, and it's just from experience. So happens that the smaller that number is, the greater your degree of perspective, or the focal length of your camera is an analogy. Okay, so I have a triangle, but you see it's not being closed already. So we have 3 points, and it's connecting those points, but we need to close path, and that's just a little canvas trick. It's going to close the triangle for us. And you'll see in the math here, I've got 2 pi divided by 3. I've got I equals 3. It counts down to 0. So we're working with 3 at this point. 3 is our magic number, and it's drawing a triangle. Go figure. But maybe we don't want a triangle. So I'm adding to the angle, which is p. Pi divided by 3 reorients the triangle upward, versus downward, how it was by default. But maybe we want a square, because we're going for a cube. Let's just do a cube. How would we do that? How would we turn the triangle into a square? Well, 3 just needs to become a 4, and I needs to go from 4 to 0, rather than 3 to 0. So I'm doing a little bit of color work here. There's an interesting little hack to these hex codes for color. If you add the 4th bit, it's alpha, the alpha channel, so you can have some fun with that. And it's 0 to 16. After 9, it goes A, B, C, D, E, F. Excuse me. And that determines the opacity, how transparent it is or not. So remember, T is our counter, right? It's counting up from 0 from the time the program starts by 1/60th of a second per frame. So if we add t to our angle, it rotates the triangle. That's what you just saw there. So now we want to figure out a square, because this triangle is great, but we're doing a cube. So let's see. Before we get to a cube, we need perhaps more than one dimension, right? So we're working in 2 dimensions, obviously. It's a 2-dimensional triangle. We want 2 of them to start with, just to move forward. So I added another nested loop, or the I has become a nested loop. J is now the parent loop. And I made Z involve J. So our z values, our z coordinates, excuse me, are dependent on j, which means that there's an element of depth now because we're drawing it twice, and the depth is changing on the second iteration. But it's not quite a cube yet, is it? So we need to change 3 to 4, and in fact, instead of having to change all the 3's to 4's every time, let's just assign a variable. It's going to be SD, sides, whatever SD means to you, and SD is now 4, and we have a cube, or excuse me, a square. It's not quite a cube yet. The spacing is off, and we don't have enough sides, obviously. So it's looking closer. But we have okay. So some of these rotations. So pitch is what you would expect. You're pitching forward or backward. It's like the word suggests. Yaw is lateral rotation. Roll is like if you're rolling this way. And it's you can do them all together or none at all. It's totally up to you. And if we want to get the spacing right, now this is an interesting thing that you may have learned in school, maybe you don't remember, maybe you never took the class, but the Pythagorean theorem shows you that the length of a hypotenuse is equal to the square root of the sums of the squares of the other side. So we can figure out, I'm not going to go through all of it, but you want your square to be the size of the square in a cube needs to be a function of the square root of the hypotenuse. So I'm going to just add that real quick here, and I'm going to make a variable name for it. ls. I don't know. These variables are constant for me. I use them constantly, and they mean the same thing from one program to the next. You see, we have some spacing problem here, so I need to fix that. And I'm going to create a variable called ls to define the size. And you just take the square root of 2, and you multiply your size by it. So it's a factor, right? It's a scale. You can scale the whole cube or just one little piece of it. It's kind of an in-depth math course, but so now we have ls, which is 4. So that's what 4 looks like, but we're going to need to multiply it by this, is what I'm telling you. So it's the times 0.5 is a square root. So times is to a power, and to the power of a half, 0.5, is a square root. It just turns out that it is. So if you have 2, the square root of 2 times ls, which is 4, it just so happens to work out that the size is what we need. And you can see it, you can experiment and try it out for yourself. We're still missing 2 sides here, but you see how this is going to go, and I'm not going to actually fill in those 2 sides in this video, but that's the essence of it. And there's a couple of other little hacks, and I'll make some other videos, but this one's covered a lot of territory already. So the round line cap and line join just cleaned up the edges of the lines. Sometimes you get these little artifacts if there's a sharp bend in it, and if you round it off, if there's a performance hit for rounding if you have a lot of lines, but it makes it cleaner looking. So it's kind of a decision you got to make in graphics. But that's the essence of that. So again, I'm going to put my contact information and a link to this demo. You can fork it. It's free, public domain stuff. Help yourself. And I will look forward to the next video, and hopefully you will as well. Have a great day.